This was self-attention, but actually we can improve self-attention by using this idea of multiple heads, which basically means that we just run self-attention more than once. So let's say that we want 2 heads, which is the example that I will show. It means that I will run self-attention twice and then somehow merge the results. And why we do that? Well, it's because in many of these problems, let's take natural language processing, for example, there are many kinds of relationships that we can have between the elements. Like in natural language processing, we can have subject, object, verb, which is one kind of relationship. We can have pronouns that we want to solve, like it, which is referring to a particular object. This is another kind of relationship that we want to extract. And if we have more self-attention mechanisms, or more heads, every head can specialize in a particular kind of relationship. And we will see this actually in a visualization later on. And how do we, so how can we implement that? I said that I will just run the self-attention more times. In this example, I'm only using 2 heads, but you see that, let's say we focus on just one head, head 0. You see that the equation is exactly the same that you saw before. So we are doing exactly the same thing. We are computing the weights, we are computing the weighted sum, and we are ending up with this encoded version H0. And the other head will do exactly the same. So it will compute the weights, it will do the weighted sum, and come up with this encoded version H1. At this point, you may have the question why we end up with 2 different results if we do the same thing. And the reason is that it lies in how we compute the weights. I will go more in details in the next slide. But the intuition is that every head will specialize in extracting some particular kind of relationship. And once we have all these encoded states, in this case only 2, we just put them together. So we can, for example, concatenate them and end up with the final encoded state H0 here. That is what we wanted to compute. So at this point, there is still the question why the 2 heads, they are producing different results. And the reason is that every, you see here, so here, let's say we want to compute the weight for 2 words. In this example, x3, x4. These 2 words are represented as vectors here. And we will see in the natural language processing presentation that this is a very natural, a very common way to represent words in that field. And you see here we have these 2 vectors. But before computing the dot product, for every attention head, we will project the vector from the original space into a different space. And this projection is, will be learned by the model. So I don't need to specify that. We just hope that the model will learn to project these words in a way that will capture some particular kind of relationships. And you see now that the projection from the head 0 is different from the projection from head 1. And now if you compute the dot product, you end up with different results from the case 0 from the case 1. And that's why we end up with different words for every head. And obviously at that point, once I have the weight, I just do the weighted sum, and we are done. OK, so let's look a little bit at visualization of what self-attention is doing. So in this case, the first thing to notice is that here you have a sequence, and here you have the same sequence. Because here we are not dealing with the general idea of attention that we saw before with machine translation. Here we are using attention on the same sequence. So you see that here we have the word it's, and we are trying to visualize where is self-attention looking at when it's producing this new encoded version of this word. And you see that actually I have 2 heads here. One is purple, which is only looking at the word low, which is the one that is referred by it. And here instead, you see that this other head, the brown one, is a little bit more broad. It's looking at the word law, but also at the word application. So you can see how every head can specialize in trying to extract some kind of relationships, and then we can put all of them together to create this new encoded representation. So at this point, there is only one thing left to do. We mentioned two problems at the beginning, if you remember, that RNN are not easy to parallelize, and they are not good with, if we have very, very long sequences. Let's see what happens now that we have the transformer architecture. So for the parallelize problem, it is actually solved because if you have seen how we apply self-attention, it only depends on the input sequence. It doesn't depend anymore on the previous internal state or the next one. So there is no interaction between these encoded versions. So H0, H1, H2, they don't. They are not used in the interaction between these elements is not used when we try to came up when we apply the equation to came up with these various H. And because of this, I can run all of them in parallel. Because the input sequence is available to me, I can just run all of them in parallel. And this is great because on a GPU, this means that if I have a nice GPU, it will run all of these steps at the same time. And now instead of taking, I don't know, 5 seconds, I can take only one. Well, it's not exactly linear, but you get the idea. So we don't have anymore this problem of the chain, of this chain of computation that was there with the RNN. Second problem was these long-term dependencies. And now we don't have this problem anymore. So this problem was there because in the RNN, let's say that we have this element x5 here, and we want to extract information that comes from x5, but also x0. This was and let's say here I have a lot of steps. This was a problem with RNN because the information has to flow all over the intermediate steps. And maybe I will lose the information along the way. But with this idea of self-attention, we don't have anymore this nature where I have to go all over the elements. I just apply this weighted sum. So in this case, in the case of x5, we can say that x5 can get information from x4 and x0 in the same way. Like, it's not anymore that x0 now is penalized with respect to x4 just because it's far away in time. So you can see that here too, the self-attention is providing some advantages.